C'est un grand plaisir pour moi de vous présenter le professeur Hagit Atiyah du Technion en Israël. Ceux d'entre vous qui étaient ma leçon inaugurale se rappellent que j'ai insisté sur le fait que le monde de l'algorithmique répartie... il ne marche pas. Que le monde de l'algorithmique répartie est un monde principalement de femmes. Les grands résultats de ce domaine ont été établis en particulier par Nancy Lynch, que j'ai mentionné, et Hagit Atiyah, qui nous a fait la gentillesse d'être ici aujourd'hui. Donc, elle a travaillé à un moment donné au MIT, comme beaucoup de gens qui travaillent dans l'algorithmique répartie. Elle a aussi travaillé dans la prestigieuse École polytechnique fédérale de Lausanne pendant un petit moment. Et donc, je vous la laisse vous parler de coordination sans agrément.
Thank you. I have to speak in English. My French hardly allowed me to follow the previous talk. Thank you, Rashid, for inviting me to speak here. Thanks to all the audience for coming here, especially people from the distributed computing community in Paris, which I realize how large it is now. Okay, I'm gonna continue in some way where Rashid stopped and talk about atomic snapshots and take it to a little higher level and more advanced. And I'm gonna do more or less three things about atomic snapshots. One, I wanna try to view them in a way that is somewhat different than the way that Rashid viewed atomic snapshots. And using this different view, we will be able to find more efficient algorithms and to understand, give a hint, how they can be used to implement interesting objects that are quite useful in practice. And lastly, I will show how atomic snapshots are useful in solving other problems, and in a particular other problem that is quite interesting by itself. Not extremely useful, but I think quite interesting, and I'll give you a hint why at the end of my talk. Okay. So as I said, the first thing I want to do is to help you think about atomic snapshots in a different way than the way Rashid talked about them. And rather than think about them as a way to take operations that have to be linearized in time, I want to think about them as what we usually call a decision task. Okay? So a decision task is a situation where we start with a value, and when we complete, we have to output another value. So each process starts with a value, does some computation. Other processes might be doing their computation and concurrently with that process. And at the end, each of them, or whoever terminates, outputs a value. And we're going to think first about a single-shot snapshot. And I want to find an analog decision task for it. So the analog decision task will be based on set inclusion. Okay? So think that instead of, I write things, I read things, I need to scan, what I do is I start with my own value. I do this just once. I start with a value. And then I do some computation. Other processes might be doing their computation at the same time. And then at the end, each of us has to output a set. Okay? My set, of course, should include my own value, because I'm there. I definitely need to know the values. So I need to output a set of values. All of them should be values that some other process started with. And for simplicity, let's think that either I have the value of the other process or I don't have the value, because there are no lying or cheating. So either I got your value or I didn't get it. Okay, and there's only one value so far. And so I start with the value. I collect some subset of the other process's values, okay, including, of course, my own. And the important property, the additional non-trivial property that I want to add, is the property that the sets that we output, they are not necessarily the same, but they need to be comparable by inclusion. Okay? So that's the property I have. Each process starts with an input. It's not necessarily A1 for P1, etc. But we get some values input into this box, this decision task. Okay? And each process outputs a set of values, again, including its own and only values that were introduced into the system. And the property we need to ensure, the important property we need to ensure, is that the sets that we output are comparable by inclusion, can be ordered by inclusion. So it's not possible that I start with A and another thread starts with B, and I will end with A, and the other thread will end with just A, and with just B, sorry. Okay, that's of course not comparable. These sets are not included in each other. And I argue that if we were, so I argue two things actually. I argue that this decision task is equivalent to doing a snapshot just once. Okay, a snapshot that you update only once. Okay, obviously if I could do a snapshot, if I have a snapshot implementation, then what I do is I write my value, I take a snapshot, and then I just take the union of the values that I got in my snapshot. And because the snapshots must be ordered, the scans must be ordered, it must be that the sets that different processes return are included in each other. Okay, so that's one direction of the equivalence. The other direction of the equivalence, okay, at least for a single shot snapshot, okay, is that if I could solve that problem, basically the way I solve snapshots is I write my value, okay, do the lattice agreement, okay, do this, solve this problem, which I'll in a minute call lattice agreement, okay, solve this problem, and then just output what I got, okay? And the reason is that I can linearize the scans in the order of inclusion. Okay? This can be made more precise and formal, but essentially it's a fairly simple analog. And again, and we call this decision task lattice agreement because we think of the lattice of sets and subsets. Okay? So this is this problem. Okay, so some examples. So, for example, if I start with these values, each process starts with a different value here. You can think of its identifier or whatever. Then this is a good decision. This is a correct output for the lattice agreement. So B just outputs its own value. A actually manages to read the three other values. And two processes actually end up with reading everything. Now, the good thing about lattice agreement is actually it allows us to think about taking a snapshot or solving lattice agreement or one-shot snapshots by doing things in an incremental way. We can break the task up. Okay? So instead of having everything nicely ordered, like I defined lattice agreement, let's say that we manage to get some order in the outputs that we have. Okay, so it's an intermediate problem. So again, we have processes. They start with the inputs. Now we'll do a slight generalization. And instead of starting just with your own value, you start with a set of values. Think about it as you write your value, you do a collect, and you have some subset of values. But after you do a collect, sets are incomparable. Okay, you should realize that. So if you just write and do a collect, the sets that you read are incomparable. So you do a write, collect, you have a set, okay, and you start working with this set now. And so each process starts with a set. And then when we end the decision task, our decision task, what we have is we partition the processes into two subsets. And for some inexplicable reason, but historical, so I'll stick with it. We have one subset that are what we call the masters, and another that we call the slaves. Slaves are really simple-minded. Okay, the simple-minded slaves, all they do is actually they output the same thing that they started the decision task with. So they come in with some subset UI, and they go out with the same subset VI. They learn nothing, okay? They are the imbeciles, maybe. Okay, they go through the decision task, and they learn nothing. The masters go through the decision task that is called a classifier, and the masters learn. What they learn? Essentially, first of all, of course, they keep their knowledge, okay? So they know everything they started with. So UI is included in VI, the output set they output. Also, they learn everything that the slaves had, okay? So basically, we union. So for every slave, its output or an input is included in the output of the master. So masters learn everything that the slaves knew. Okay. So that's the two important properties. The other thing that we want to do is that we want the size of the knowledge that the masters have to be bounded from below. Okay? So the slaves, so for some parameter k, that is part of what we do. So we parameterize the problem with a parameter k. And we know that all masters are knowledgeable. Okay, so they know their sets, the sets they output are at least of size k. Let's see a simple example. So a simple example is when the parameter we have is n. Okay, so when we can have this parameter be a, k that I had before be n. And then the masters, if you are a master, you output the classifier knowing everything, knowing all n values that were entered. And the slaves, well, they, actually that's a mistake I see here, but the slaves go out with the values, there's actually some mistakes here. The slaves go out with learning nothing and the values they had before. Okay, this is correct. Okay. You could also parameterize with a smaller number, like n-half, okay, where n is the number of processes. This is, in distributed computing, n is always just the number of processes. N is never anything else, and the number of processes is almost never any other thing. So this is like almost a given. Okay, so I can have the parameter of the classifier be n-half, and then the masters could learn either this is like for 4 processes, either learn everything, you could be a master and learn everything, or you could be a master and know more than half, like here, 3 values. Okay? And as before, again, I see a mistake. As before, the slaves learn nothing from going through the classifier. Okay. Why is this interesting? This is a classifier by itself is not very interesting, but we'll see later that it can be used to, by putting several classifiers together, we can solve a lattice agreement. And I think some of you might see a hint. So a nice thing about the classifier is that it's actually very easy to implement it. So how do you do that? What you do is you go into this is really just the code. You write your input set, then you go and read all the sets of the other processes. You union them. If it's large, if the size of the union is large, more than k, you declare yourself a master. But before you leave, you reread everything again. Okay, so you reread everything again. And now you're sure you'll get more than k, because you already saw k before. So maybe you'll see some new values. Okay, and then you return their union as your VI. And if you didn't see a lot of values, you just output what you came in with, your initial set, your input set. Now, it's important to note that I'm not claiming or arguing that the number of masters is going to be more than k, or like if it's n-half, I'm not going to have at least n-half masters, and I'm not, actually I will, but I'm not arguing anything about the number of processes that will be in each class. Okay, would either be either masters or slaves, although we can bound them. But I am arguing about the amount of information they get out of this classifier. Okay, so all the arguments are about the sets, not about the number of processes in each class. Now, actually, something you could see, or you should be able to argue, is that there cannot be more than k slaves. Okay, because at most k processes will be able to leave this decision task without learning more than k values. Okay, so think about the first, at most the first k processes to write can be slaves. Anybody else must see more than k values, hence it will be a master. But it is possible that everybody will go and be a master. Okay, so it is possible that we all write kind of together in some sense, and then we all read and we all see everything and we go out. Okay, as masters. That's not an interesting case, but and we cannot be sure that it will happen, but it can happen. Okay, and the other thing to note is that just doing this takes you about n steps. Just one write, reading everything, and then reading everything perhaps. Okay. So again, the example is botched, but so again, let's assume we've done this classifier once and with a parameter of n². Now, what you should notice that actually the way the outputs that we have for the masters are already ordered by containment. The slaves are not. Okay? So what I can do is now I can go to the slaves, okay, and tell them, you know what? Now do the classifier again, but now with a parameter of n². Okay, so for this will be 1. Okay, now they go in. Think about the program we've seen before. I do the same program as before, but instead of k being n², k is now n². Again, 1 essentially. So they'll both go in, they'll write their value, okay? They'll read everything, okay? Now we have two processes going into this classifier, okay? The second of them, the one that writes last, will necessarily see at least 2 values. So one of them will go out, at most one of them will go out with its own value. The other will go out with the 2 values. Now they are comparable. Now there's inclusion. Maybe both of them will go out with the same 2 values. That's fine. Maybe one of them will go out with its own value and the other will go out with 2 values. But it's not possible for both of them to go out with their own value as before. So it's not possible that both of them will go out as slaves, learning nothing. One of them will learn everything, which is 2 values in this case. The other maybe learn everything or will stay with its own value. What we have now, essentially, is that the values are contained, are ordered by inclusion, and we've essentially solved lattice agreement for 4 processes. A small example, of course. But this hints at how we can solve lattice agreement for a general n. And that's the old classical computer science thing is of branch and bound, essentially. So what I do is I get all the processes to start with a classifier whose parameter is n². And then they are partitioned into masters and slaves. Again, I don't know how many processes exactly go in each set. At most, n² are slaves, but maybe everybody or 3/4 of n are masters. We don't know. Okay? But we know that they all know at least n² of the values. Okay, so we don't know how many they are, but we know how much they know. Okay? And with that, those who went up, the masters, go through a classifier of 3/4 of n. And again, some of them will learn at least 3/4 of n. Others will know less, but all of them will still know at least n². Okay, so we are narrowing the number of values, or the range of values they know. So all of them know at least n². All the I don't know if I have that here. Yeah. So think about the slaves, those who were first masters, then slaves. Okay? All of them know at least n-half values, and they know everything that goes down here. Okay? Now, everything they know at most, each of them knows at most 3/4 of n. And everything they know is included at what the processes that were masters know. Okay? And then we just continue. We have another layer. We, again, partition the ranges into half, and so on and so forth. And by these arguments about inclusion and about the size of information that processes have, we can basically squeeze the amount of information processes that follow the same path can have. The difference, the discrepancy in information that processes that follow the same path have. And by the time we do log n minus 1 layers of this thing, we end up in the situation where the classifiers, I actually put here an extra layer that is not necessary, but it's easier to think this way. So we have we end in the situation that at the last layer, the classifiers are numbered by consecutive numbers. The parameters are consecutive. And thinking about the values, it means that if I'm here at L, what I have, if a process that ends here knows everything down here, okay, and knows at least L values. And everything it knows is included in what processes here know. And they know at least L plus 1 values. So essentially, the possible discrepancy that we have is so small that everybody who ends up at the same classifier knows the same set. Okay? And the sets, whoever ends up, the sets are ordered by inclusion from bottom to top. Okay? Actually, proving this takes more work, but if you work with the formal properties of the classifier that I've stated, you just do this by induction, and it's actually not very complicated. Okay? If you do set the right invariants. And the good thing about this algorithm is that it means that you can do snapshots in n log n operations, because each classifier takes you order of n steps, and you have log n steps of that. Okay. Now, we can think of snapshots also as lattice agreement, what is called generalized lattice agreement, and it's a longer sequence of values. You could think of processes that get a stream of values, okay? And then each process must output a set of values. This set of values must include all its prior values, okay? And the sets must be comparable. And of course, you never output something that was not generated in the system. There are no fake values or whatever. And in truth, you really need to optimize and have also a read operation, something that just reads the state of the system without introducing a new value, but that's an optimization. And for simplicity, we can always say that I introduce a value and I read everything. Okay, that's at least if we don't care so much about efficiency, that's good enough. So again, this thing corresponds very easily, if you don't care about complexity, corresponds to snapshots, because I can have this array of values that I'm snapshotting, and in each component I have a set, basically the set of values that a particular process have received. And then you take a snapshot of this array, you union it, and then necessarily, if you had a snapshot, if you are taking just snapshots, the sets are going to be comparable. And this can be called the generalized lattice agreement, because we can think of it as moving on a very big lattice and making sure that wherever we are, the values that processes output are comparable to each other. Now I'm going to be a bit more high level and a bit not detailed, and you probably would not totally. So the nice thing about generalized lattice agreement is that you could actually implement generalized lattice agreement from lattice agreement, the single shot lattice agreement that we had before, or any other algorithm. And the way you do it is you take, again, if you don't care about complexity, is you take an infinite number of copies of lattice agreement, and you work on them. And it repeats an idea, actually, the idea that we've seen twice in Rashid's talk, if I understood everything you said in French correctly. And it basically, what we want to do is the following thing. So we have these copies of lattice agreement, and processes basically try to go to work in the same copy of a single shot lattice agreement. Okay, so I start, I see where the action is, okay, and I see which copy of lattice agreement is now active, and I go and work, basically introduce my new values to this copy of the single shot lattice agreement. Now, ideally, if we were coming like in a lockstep or some synchronized manner, this will be enough. We come together, we go to the same lattice agreement, we organize ourselves, we get the values, and we go out. But it is possible that I'll go to certain value, to a certain copy of the lattice agreement, and meanwhile, the whole world around me will change several times, and people and other processes will move to newer and newer copies of the lattice agreement. Okay? And then it's not absolutely simple for me to return the value of my lattice agreement, what I did. So the idea is basically that this can happen. Okay? And if this happens, I say, okay, too bad. And then I'll just try again. Okay? And this can happen again. I mean, I could go to another lattice agreement, another copy of lattice agreement, do the work there, and hope that things will work. But when I finish my work in this other copy, the later copy, I look around, and again, lots of people, lots of values were introduced, and the world has changed, and everybody's already far ahead of me. The thing is that if this has happened, okay, if this has happened, then there are lots of values of lattice agreement lying around, essentially, that I can just pick one of them, a current one, a recent one, and return it. Okay? So that's the code. So my first try, I get a new round number, basically figure out where everybody is, join this copy of lattice agreement. I need to read everything, and I need to pick up the right input value to do the lattice agreement. So I read what everybody is up to, and I union that, and I enter the new lattice agreement. And then I finish the lattice agreement, and I look around to see the counters and to see basically on which copy everybody is. And if people are still in my copy, then in some sense we have simulator, or we happen to be in the synchronized case, or sort of synchronized case. Okay? And then it's fine for me to return what I got. And if the counter, if the current lattice agreement copy has moved forward, then I say, okay, too bad, I am not doing anything. And then what I'm going to do is I'm going to do a second try. And the second try is almost identical to the first try. Okay, so you get the new, figure out the current round number, you again reread the current sets, you union them, and you just try enter the new lattice agreement where everybody is now, or where you think everybody is now, and you get the output, and you check again where everybody is. Okay, and that's where the difference starts. So up until here, it should be the same code unless I made some mistake. If nobody moved, that's the last sentence, the last command. If still everybody is in the same lattice agreement copy, then fine. It's the same situation that we somehow happen to be synchronized. Nobody moved. I was like in the first pack. And so it's like some single shot lattice agreement happened in kind of isolation without interference with the other things going around. So you just output what you got. However, if somehow, while you were doing this lattice agreement, the whole world moved forward, so again, the round numbers are more than where you were, then you say, well, forget it. I'm not going to try again. What I'm going to do is I'm going to look around and see what other people have returned and what are the last things that other people have returned. And if I'm careful enough, if I pick a recent, there should be around, I mean, the argument that we need to argue is that there is around a recent value that is good for you to return. And the reason is that if everything moved and moved at least twice, okay, then at least somebody who moved twice, okay, included in their value my set. Okay, and it's fresh enough, it's current enough for me to return it. Again, you know, really proving this needs carefulness and rigorosity, but it's actually not rocket science. It's really first order and elementary arguments. So it's okay to return this value because this value is recent enough and it includes my set that I have tried to introduce into the system. Okay. So why generalized lattice agreement, or in its other name, atomic snapshots, are interesting is because you can do lots of interesting other objects with it. So Rashid has essentially showed you how you do counters with snapshots, okay? And you do what's commonly called the grow-only counter. So the counter just grows. It's not a counter that you can decrement. Okay. And if you want to, you can also do what's called a grow-only set, a set that you only have inserts. Because in some sense, the counter and the set are really the same thing. You're not just counting things, but you can also remember which things were introduced. That's almost trivial from generalized lattice agreement, because we have the set of values that were introduced. Interestingly enough, so all these two objects, and I'll show you a few more later, are examples of what's called commutative replicated data types, CRDTs. And these are sets, so I didn't know Mark will be here, but I did warn him that he'll get a shout out. So CRDTs basically are data structures where the state of the data structure depends only on the set of operations that happened on that were applied to the data object. And if we want to be able to order the operations, the property that we need to maintain is that the sets of operations that I have are inclusive, are ordered by containment. Okay? And once we have that, we can associate each operation. So we associate each operation with the set of prior operations that it assumes or implies. And then we can just linearize the operations in the order of inclusion. And these are two examples, but actually you can do quite sophisticated things if you think in a creative way. So for example, you can have what's called a two-phase set that can grow and shrink, but instead of, but you assume that the deleted element is never reinserted. So you have the sets of things that were inserted, and there are things that can be deleted. But if you delete something, you never reinsert it. And then you can represent this one as the set by two grow-only sets, one of the inserted elements and another of the deleted elements. And you can even have some way to reintroduce elements by time-stamping them correctly. And you can also observe remove sets, and there are various things. All these are very, very useful data structures to have when you build concurrent systems. And I really recommend to go and ask Mark about that. Let me somewhat say it more precisely. So we have a data type, a data structure, and let's assume it has just one operation. And so what we want to have is the operation to be commutative, so it doesn't matter in which order the operation happens. And it has to be associative, so no matter in which order I group the elements. And it also has to be idempotent. And then if you have that properties, then clearly the state of the data structure depends not on where exactly the operations happened, but what was the set of operations that happened. And again, in order to linearize, you need a set inclusion property. Okay, so you can associate basically the operation with the set of prior operations. And if these prior operations are ordered by inclusion, then you can linearize them quite easily by the inclusion order. I have in here another example that I worked on in recent years, which is something called the list object. And the list object allows you to insert elements in various, you have a list, and you are allowed to insert elements in various positions in the list, and you have an operation that actually reads the whole list. And you have the natural property that each operation has, each operation returns a list of elements that were priorly inserted and not deleted yet. And it can be represented as CRDT, but the interesting property about this object is that it can be used to model a very rudimentary, to provide very rudimentary support for collaborative text editing, like Google Docs and wikis. Okay, so I will not go into the details of working with list elements, with list data objects, but there are a particular kind of CRDTs with its own properties that can be used for optimization and can in turn be built on top of generalized lattice agreement. Okay, so I want to, this will kind of conclude the main part of my presentation about what to do with the snapshots. Let me just say that the best snapshots we have require order of n reads and writes, but they use what's called multi-writer, multi-reader registers. Basically, the algorithm that I've shown you, which ends up giving n log n atomic snapshots, is the best we know to do from single writer, single read, multi-reader. And we don't know whether this is a lower bound. And there's lots of work on CRDTs, on generalized lattice agreement that has to do, that does various optimizations, basically to reduce the size of data that you keep, the number of messages that you send if you work in a message passing environment, the amount of computation that you do, having reads, depending on particular semantics of the object that you have, and so on and so forth. So I think you can imagine what kind of questions you can ask and what kind of answers you can answer. I am skipping here, and I think you will get to this later in the course, is the issue of working interchangeably. And I think you mentioned that in your French things you said in French, but I'm not sure. So maybe you said this already. But I am doing something very deliberate, and something that I actually believe in is I mix discussion of shared memory and message passing systems. I mix the discussion of systems where concurrency comes from multi-threading within a multiprocessor or even a single processor system, and systems where concurrency comes from large-scale concurrency, like multi-core servers, maybe even geographically distributed. Because many of the ideas that we have go between these different scales. And I believe at some point you'll get to see that it can even be said in a very precise way. Okay, so coming back to the title of my talk, why coordination without agreement? So coordination, if you go to like the online dictionary, says you organize elements in a complex body of activity and help them work together effectively. And the examples they give contains the word agreement. We need to agree what to do. Okay? But I hope the example of lattice agreement that I've shown you, although it has the word agreement in its title, doesn't really have agreement. I mean, it's not like I know what other processes which set their output exactly. Okay, I know that somebody will output everything, yes, But actually, besides this, I'm not sure I know anything about what others will be outputting. All I know when I do lattice agreement and generalized lattice agreement is that their sets will be comparable to mine. They will either be included in my set or my set will be included in their set. Okay? So I can coordinate with them and even implement quite interesting and useful data structures by just making sure that our sets are comparable. We never really agree on anything, but we make sure we are comparable. Let me give you another example of how we can do coordination, not by agreement, but by basically getting out of each other's way. Okay? So this whole talk is a trip down memory lane because I'm really speaking about work I've done in my PhD and shortly there. I mean, most of it is in my PhD or shortly thereafter. And so here's the example. This is like a pictorial example. Think that you have, you know, like you're managing a big airport. Let's say Charles de Gaulle, and or actually Tel Aviv Ben Gurion Airport, which just the other day, 2 airplanes were almost flying at the same flight route, okay, landing route. So we want to make sure that airplanes are flying in different heights and not flying into each other, okay? Now, one way we could have done this is assign prior number to each airplane, okay? And say if you're plane number 15, you always fly at level 15. Now, but if we have the whole world of airplanes, this will be like millions or whatever, and then we just don't have, you know, the sky is high, but it's not that high. And I mean, even if the sky is very high, airplanes cannot go to level million, okay? So what we want to do is say, okay, planes have different names, numbers, but we give them a new name or a new number that tells them where they are going to fly in the way that each of them flies in a different level. Okay, and they'll never bump into each other. So this is what I call coordination by getting it out of each other's way. So it's a problem called renaming. And we have a small set of processes that participate, like the number of the airplanes that are at each particular point at the particular airport. But they are actually coming, they are drawn from a much bigger subset, like all the possible airplanes in the world. And so that's why they have long identifiers, long names, big names. Okay. And then we want to assign to each of them a new name. This is the level that they are going to be flying at. And ideally, we want the number of levels, to be proportional to the number of planes that are actually flying. Okay? And obviously, because our planes cannot go very far in the sky, we want the smallest possible range. And you can, there are 2 flavors of that problem. One is called adaptive, and the other is called non-adaptive. In the adaptive version, the number of levels is actually proportional to the number of airplanes, for example, that you currently have in the airport. In the non-adaptive case, you have a bound on the number of airplanes that could be at the airport at each particular time, and the names are proportional to the number of this upper bound. And doing renaming is, well, you know, it's doing a safe version of renaming, a non-terminating version of renaming is not very complicated if you have snapshots, okay? So what you do is you basically pick a name. You say, oh, I'm going to be number 1. My new name is going to be number 1. And then I declare, I announce that this is the name I want for myself. So I write my full name, and I say, and I want number 1. And then I repeatedly do a scan. I read everybody's names and new names. And then I check if anybody wants the same name that I wanted. If nobody competes with me on the same name, if nobody suggested 1, then I say, excellent, I'm going to return 1, or whatever number that I have proposed now. So I return and decide on this new name. And if there's other processes suggesting the same name, what I do is I basically look at all the other processes. I rank them. So I see who's around, and I rank them by their original names. Also I cross out every name that is currently suggested. So I cross out everything that is currently suggested. And if something, and if my rank is, if my rank is k, then I take the kth free place, the kth name that is not suggested, and this is my new suggestion. So, for example, here I have both process 2 and process 3 suggested 1. That was their initial suggestion. And somebody had suggested already 2 for some reason. And both of them read, for example, and they see that 1 is suggested. And let's say they both see the same set of values. Both see 1 suggested. So 2 knows that it's the lowest ranked process currently participating. It's going to suggest number 3. 3 sees itself as the second ranked process, so it's going to suggest 4. Yeah, so that's what will happen, okay? And we go this way until I suggest something and nobody suggests the same thing. And when this happens, I decide. Okay? Now, with snapshots, it's quite easy to see that the new names are unique. So never two processes end up deciding on the same new name. And the reason is that I first declare what I want and I check. And then I declare what I want and I check. Okay, so if two processes suggested, so it relies on snapshot properties, because if two processes end up deciding on the same value, it must be that they both scanned before that. Okay, and because the snapshots are ordered, one of them has the latest snapshot and will include the suggestion of the other one, and it will not decide on the same value. Okay, so if we assume a contradiction, if two processes take the same name, it must be that one of them will see the other and will give up on this name. So that's uniqueness. It's also possible to see that the new namespace that we get is at most 2n-1, because whatever name I'm suggesting is I cross out n-1 names that are suggested by the others. I never have my own value to cross out. Okay? And then I go at most n, because that will be my rank. And in fact, it's not just 2n-1, it's, you can even argue that it's 2k-1 if there are k participants, if only k processes are taking part. The hardest thing to argue, which I will not even hint at, is termination. Okay, why this thing eventually settles down. And the idea is that at the end, at some point, processes stop joining, and then the lowest process eventually, the lowest undecided process eventually gets a name and gets out of the game, and so on and so forth. So that's what I wanted to say about renaming. It's a very interesting problem, definitely when you look at the long-lived version of it. And seemingly, I think, benign and naive question, obvious question really, is whether 2k-1 or 2n-1 is the optimal namespace. I don't know how much I think you're going to go into near where it is. Answering this question actually ended up being quite a roller coaster. And it led to quite interesting research relating distributed computing to topology and various things. The jury's still out on some of the answers here, actually. So these are citations for the papers that I mentioned, in case you want to follow and read the details. And with that, I will conclude. And thank you.